Welcome to Thought Kernel, where we break down educational concepts in different fields to understand them deeply and their connections that form our modern understandings. You're in the right place to learn, so let's get started. Today we are going over a deceivingly simple idea in physics, Hooke's law, the foundation to many ideas in physics from classical to quantum. Let's crack it open. First, what is Hooke's law? Well, Hooke's law is a principle that states the force required to extend or compress a spring by some distance is proportional to that distance. Imagine a spring hanging from a stationary surface with a ball on the other end with some mass. Then you pull it 1 inch downward from its resting point, and you notice it snap back up. Then you pull it downward 4 inches and notice a much faster snap of the spring. This is Hooke's law. An important aspect in Hooke's law is equilibrium, or the resting point. The spring will use restorative forces proportional to the displacement of it from its equilibrium point to return the ball to its original location on the spring. As we know from Newton's law, the equilibrium point is where the forces acting on the spring are balanced, and in this case, its displacement is zero. Furthermore, the force the spring applies to return to equilibrium point is labeled as a restoring force, bringing it back to balance. Likewise, proportionality in Hooke's law is often stated as the more you stretch or compress a spring, the harder it pulls or pushes back, and this highlights the proportionality that is essential to Hooke's law for understanding the relationship between the force and displacement of a spring. We will see how they are proportional with the diagram in a second. Not to mention, noticing the formula proportionality between F and X in the equation allows us to solve for the spring constant of K. The spring we are dealing with could have any varying value of K, the spring constant, which in turn means its stiffness, where a higher K means stiffer, like a car suspension, or a much smaller K could mean something as non-compressive as like a slinky. Now, here are some examples. Now, the proportionality diagram highlights that the difference in X multiplied by 2 simultaneously multiplies the force by 2 as well, just touching on the proportionality that any change in X is equal to the change in the force. And the force extension graph displays the linear relationship of the force and displacement building on top of the foundational concepts of Hooke's law, where the slope is also the spring constant, K, where the varying slope will determine the different stiffness of the spring. So now that we have defined Hooke's law, we will be diving into the real-world context of Hooke's law and its ubiquitous presence. Hooke's law is woven into physics, providing an understanding of elastic behavior, which developed a framework for understanding elasticity. Similarly, the movement of springs produces a sequence of harmonic motion, as I'm sure you all have noticed before, whether or not you thought of Hooke's law when watching its rhythmic movement. It is simple harmonic motion. However, it may come as a surprise, it has also provided help towards the microscopic world of the quantum harmonic oscillator, which provided insight to further quantum theory and an analytical solution to one of the quantum equations. And a less known region of physics, acoustics, where Hooke's law understands the springiness of atoms to transfer sound waves. The elasticity of materials. Notably, materials can be categorized by their ability to return to their original state following deformation, hence elastic, while their counterparts, plastic, are materials in which they cannot return to their original state from a deforming force. Hence, elasticity is the ability to deform and return. However, elasticity can be further explained by stress and strain. Stress is the force per area acting on the object, and strain is the measure of how much the material deforms to the force. Kind of sounds like force and displacement, right? Essentially think of Hooke's law of forces on objects and their reaction in distance, but with objects to support buildings or other objects outside of springs that could apply. To help you build an even deeper connection to the Young modulus is essential to building the connection between Hooke's law and elasticity. The Young modulus can be seen on the graph to the right. The graph slope up to the proportionality limit represents the stiffness constant of the object under stress and strain. This is exactly the spring constant shown earlier. Realizing elasticity is very similar to Hooke's law provides beneficial understandings to both aspects with a dip into the real world. Diving deeper into the motion of Hooke's law, we have simple harmonic motion, also referred to as SHM at times. Simple harmonic motion is a back and forth motion that occurs when an object's restoring force is directly proportional to the displacement from equilibrium. Therefore, in a vacuum where there are no other acting forces, its motion would continue back and forth towards equilibrium forever, such as a pendulum in a vacuum would continue using forces to try to return to its equilibrium, as shown in the top left, where it would swing back and forth forever. And this is the harmony behind it, a visual rhythm with repeating displacements on different sides of the equilibrium point. Simple harmonic motion is sinusoidal behavior, which means its graph is represented by a sine wave. Imagine if the blue cube in the bottom left was moving back and forth after being compressed. Notice its movement. Its movement through time provides a sinusoidal wave, which turns to the side, exactly matches a sine wave, highlighting its sinusoidal behavior and why it's graphed like that. This is visualizing the simple harmonic motion in its proportional continuous back and forth motion. Another example I envisioned was the door stoppers that stop doors flinging like crazy when someone flicked it, as it would swing back and forth trying to return to that one equilibrium point. Essentially, Hooke's law is how we understand simple harmonic motion. Under magnification, Hooke's law adapts to the differences of the quantum world, changing from its traditions to match the probability of quantum energy. First off, the elastic potential energy is represented as the function u of x equals 1/2 k times x squared. This is the energy stored in a spring by Hooke's law. It describes how a string will resist stretches, which cause its application to understanding quantum energy, probability, and waves. The elastic potential energy provides a precise analytical solution to the Schrödinger equation as stated, which means no estimations in a world full of uncertainty. This emphasizes what is sought from applying Hooke's law to quantum physics. For understanding, the Schrödinger equation is essentially an equation for how a particle moves under a parabolic potential, as the equation for the potential energy in the Schrödinger equation is mapped as a parabola on a graph. Parabolic potential energy equation establishes understanding in the Schrödinger equation and displays the quantized energy of the quantum harmonic oscillator. What this means is that the particle's movement only exists at discrete specific values, which can be seen by the different levels shown on the diagram in the bottom right. Diving further into the parabola's benefits to quantum physics, it perfectly highlights zero-point energy, which means that even at a particle's lowest energy level, it is still moving or fluctuating. It is never fully in the bottom of that parabola, as it always has some type of energy. Hooke's law provided the potential energy to give one of the clearest solutions to an equation in quantum physics that can be exactly solved. Moving on, acoustics is less heard of, but still a vast part that makes up physics as we know it. Essentially the science of or study of sound, but what drives sound and allows it to travel. Understanding sound moves in longitudinal ways is key to acoustics, and how Hooke's law plays into the oscillation of the medium in which sound moves. Essentially, the waves oscillate in the direction of the wave propagation, and this is due to forces in the air medium and an aspect of longitudinal waves. A longitudinal wave will always oscillate in the direction of the wave propagation. But what are these forces that propel the wave propagation? Well, Hookean forces, just like Hooke's law himself, these Hookean forces allow sound waves to travel through different mediums as well, through chain reactions. Imagining air as our medium for now, the Hookean forces in collisions cause a chain reaction of movement in the direction of the oscillations, which hence is the direction of the wave propagation. Essentially, the collisions between the particles have restorative forces that pull them back to their equilibrium point after being disturbed by the vibrations of sound. So essentially, Hooke's law exists in the Hookean forces that allow us to hear everyday sounds all around us. Without Hooke's law, you wouldn't even be listening to this. Now, recapping what we covered. We dove into elasticity, which is ubiquitous in modern day, especially building, simple harmonic motion that exists behind many systems due to Hooke's law, the quantum harmonic oscillator and how Hooke's potential energy allowed for one of the few solvable quantum equations, and lastly, how we experience this today, acoustics, the vibrations that cause Hookean forces to propel sound waves. The